well, just let me know if you hear me first. So I'll try to speak loud enough anyways. But okay, so first I wanted to thank the organizers for giving me a good excuse to go more in depth into this topic. So I'll talk about, well, arithmetic. Oh, also, if I don't write big enough, just tell me. I'll try to. I'll try to write big enough, but also my handwriting is not the best, so please tell me if you can't read whatever I'm writing. And also, I wanted to say that while I have been in touch within my own research with this topic, most of the things I'm going to talk about are not stuff that I was super familiar with before, like a year or so ago. So definitely don't be shy asking questions. It can be a technical topic at sometimes. I'll try to remove everything that was not essential. I'll try to focus on the intuition behind the steps more than on the technicalities of the steps. But please just interrupt me whenever you have a question. I know also the backgrounds are different, so just tell me whenever something is not clear. Okay, so what is this? So you can first notice that I'm going to talk only about the quantum aspects of this topic. There's also a classical aspect on which I'll touch upon, but I'll mainly focus on the quantum aspects. So specifically what I'm going to talk about is the chaos that appears in specific triangles in hyperbolic space. So consider, for example, the Poincaré disk, which is one of the representations of a hyperbolic two-dimensional hyperbolic space. Say I consider the equilateral triangle on this space, which touches at infinity. Then what people noticed is that whenever you look at the quantum, say the spectral statistics of the spectrum of free motion on this background, people noticed that although it is a hyperbolic background, so you would expect that there is some chaos, what people noticed when looking at say spectral statistics was that they were seeing Poissonian statistics instead of Wiggin-Leisten statistics. So I'll go more into the details of that during the lectures, but what I want to stress is that we'll be talking about triangles in hyperbolic space, and we'll be interested in the quantum chaos aspects and probes in this space, and they show peculiar anomalous statistics. So while we would expect chaotic statistics, we seem to find integrable statistics. And the whole set of lectures will be about trying to understand, get some feeling of why that happens for these specific systems. And this system, so the equilateral triangle is one example of them, but during another example of such a system is this triangle here, and we will focus on that because it's the canonical example, and well, it'll be the simplest example to have a look at, and hopefully it'll become clear why that is. So, okay, I guess people that are interested in quantum chaos were wondering, like, okay, this seems to have peculiar features, but do we really care about like motion in hyperbolic space? Like, we're in flat space, so who cares? Is it just a mathematical thing, or does it appear in interesting contexts? And so the first part of the lecture will be to try to make clear that, in fact, this type of dynamics appear in high energy contexts as well. Namely, if you're interested in the dynamics of metric components near a space-like singularity, this type of dynamics appears. And so the first lecture will be about motivation for why we care about this, or the fact that it is realized in specific setups we might care about if you care about, say, gravity. And okay, so the first step will be to try and understand this, and then I'll explain the rest of the plan of the rest of the lectures. Okay. There has to be some erasure somewhere. I don't know where. Oh, thank you. Thank you. Okay, so of course this is just motivation. So the aim is to sketch the ideas of how we get to this type of billiard in some hyperbolic space from looking at metric components near a space like singularity. And if you don't care about gravity, this will take like maybe half an hour and then you'll be done with it. But it'll only be a sketch, so to have some ideas of where things come from. Okay, one thing that I didn't mention is that actually this type of billiards, were one of the first, I think it was the first where things like ergodicity could be proven analytically on these hyperbolic domains. So it definitely, from the classical point of view, it definitely is one of the canonical examples of chaotic motion. So it was very strange that for specific angles of this triangle, you would find some spectral statistics that is different from what you would expect from systems with a chaotic classical limit. Okay, so what we start with, so the first part is motivation. I will look at near singularity dynamics of metric components. And important, of course, there's many things to say, but there's a shortcut to see this type of dynamics appear, and that's known as the cosmological billiard picture. And so we'll only focus on that for now. Okay, so the way you do this is, of course, in gravity, you have the Einstein's equations, and the aim is to try to solve the Einstein's equations. Now, ultimately, we want the easiest way to get to this billiard picture is to have a look at what is known as the Hamiltonian constraint in gravity. So you start with some action. So now, for now, we'll focus on just the Einstein-Hilbert action. So that's just the action for pure gravity. You don't add any matter, you add nothing. We'll focus on 4 dimensions. And given this action, you can write down what the classical Hamiltonian is that corresponds to this action. And I guess this blackboard does not, oh, it does go up, okay. Okay, and so that whenever you do this, I'll write down what the metric is, and it is useful in to use a 3+1 decomposition because we're interested in the Hamiltonian. So if you don't know what the 3+1 decomposition in gravity is, it's just basically a way to split the space-time into 3-dimensional spatial slices, and then you look at the evolution of these slices, and then it's the decomposition you need to write down the Hamiltonian. Okay, and just write down the metric we'll be using. Okay, so if you don't know about the 3+1 decomposition or a Hamiltonian, this might not tell you anything, but that's not so bad. What we ultimately want is to write down the Hamiltonian. You can just believe me that this is the type of form that you need. The important thing here is that we're writing the metric components in terms of these type of scale factors, and that will be useful in the near singularity description. But at this point, you just have to believe me. Of course, in the notes, I'll give references in case you are interested, and I also gave some set of lectures last year in which these things were the central part of the lectures, so there's plenty of references that you can look up if you want to. Okay, the details are not super important. So these are 3 forms on the 3-dimensional slices. And the reason this type of decomposition is useful is that in the near singularity regime, so that means, say if you have a black hole or something, Van der Rohe diagram with some singularity here, when you go near this type of, when you go near the singularity, you can show by other means, which I'll not go into, go into, that these things here freeze. So this is related to some decomposition called Warsaw decomposition. So it has some characteristics that I'm not going to go too much into. Important thing is near the singularity, this dynamics is irrelevant. They freeze to some constant value, and the only relevant things will be these scale factors. So here you have 3 of these betas, and we'll be interested in the dynamics of these scale factors. And the way which we'll get to know these dynamics is by looking at the Hamiltonian. And if you take this metric, this action, you write down what the Hamiltonian looks like, you find something like this. Where the pi's are simply the conjugate momenta to the scale factors beta i's, defined in the usual way, where L is just the Lagrangian associated with this action. So this guy here. Okay, so at this point, what we can see is that you have some, so I haven't written down what the form of this potential is. I'm going to do that in a second. But the important intuition about this near singularity dynamics is that most of the time, this potential will turn out to be pretty much 0, negligible. And then what you have is that this Hamiltonian tells you that you have some free motion on some space. So from this space here, from the way in which the pi's are contracted here, you could write down, you could try to read off the metric. And it turns out that this metric is nothing else but a representation of the flat metric. So that's one piece of information. And so in particular, you could diagonalize this and then get the usual flat metric that you're used to, and we're going to do that in a minute. And in GR, you can, of course, write down the Hamiltonian just like you would do for any system. But because of the fact that this theory is time reparameterization invariant, it tells you that this Hamiltonian has to be 0. So this is known as a Hamiltonian constraint in gravity. If you haven't heard about it, it just comes from the fact that time reparameterization is one of the diffeomorphisms of GR, and hence it's a symmetry of theory. Your theory doesn't care about what time you're using, and hence this puts the Hamiltonian equal to 0. So that's a known fact about time reparameterization theories, invariant theories. Okay, so this is just for people who don't know much about GR. And so you end up with this equation. So this is some flat geometry where you have, so this is the kinetic term, right? And this is some potential term. Okay, so now what we know now is that most of the time this potential is irrelevant. So you just have to look at this, and this tells you that you have some free motion on flat space. So okay, I'll tell you now how to diagonalize this type of this metric, this kinetic term, so that you get a usual version of some flat metric. So basically diagonalizing this G here. Okay. And the type of transformation you have to do is looks like this. So that's just a technical exercise, right? If you want to diagonalize this Gij, and it looks like this. So I'm introducing 3 new variables for that I will exchange these betas for. And they look like this. Also, I might be making mistakes about factors of 2 or factors of I. Please don't hold that against me, but in the notes, I'll try to make everything right. And when you do this, you make this change of coordinates on metric space. You find that the Hamiltonian, which is equal to 0, looks like this now. Plus some potential, which again will be now dependent on all these 3 variables and their associated momenta. So now you can see that this is nothing else but the usual flat metric you're used to, but you have one direction which has a minus sign. So in gravity, this is usually understood to be related to change. This minus sign is related to changes in the volume. So the volume is usually associated to this negative direction, and so you see that this metric is not it's not all plus. It's a Lorentzian metric, and that means that we can interpret one of the coordinates as some time coordinates. And in the following, what we will do is basically parameterize these 2 coordinates in terms of the time coordinate by solving this constraint. And this will give us the 2-dimensional motion by interpreting one of these metric components as a time parameter and describing the motion of the other 2 in terms of that time. But we won't quite use this omega for the simple reason that although this type of parameterization is nice, it brings the kinetic term to this diagonal form we're used to. The potential is still a bit too complicated, at least for our purposes, in terms of these coordinates. So the only point of this coordinate is to bring it to the usual flat case that you're familiar with, because maybe you can see from there that it's actually, in a hidden way, a flat metric. Okay, so now we're going to do another coordinate transformation. Now that we know that this is flat space, what we will do is foliate this flat space with hyperbolic slices. Okay, and hopefully, so I'll just write down the coordinate transformation, and then hopefully in terms of how the kinetic term looks like, it will be clear that this is a hyperbolic foliation of this flat space. And then I'll finally write down what the potential terms are, and you will see, and then we will see the billiard appearing, okay? So there are just a few steps, but I hope that the logic is clear. Okay? Also, sorry, so these potential terms could also depend on these thetas, but again, it's not relevant in our story, so of course these things will have some coefficients and so on, but we won't care about it for now, and for the rest of the lectures. Okay, so now we do this hyperbolic slicing of this flat metric. And it looks something like this. So we just perform another coordinate transformation. So all of them are multiplied by some time, tau. So I'm suggestively already saying time because that's the coordinate that will have some minus sign in front of its kinetic terms. And then the rest is a bit messy, but it has a reason why it's a bit messy. So I'll come to that in a minute. Okay, so if you do this type of coordinate transformation, what happens is that this Hamiltonian gets the following form. Oh, sorry. Looking at the wrong line. Here, yeah. This is a tau, sorry. So this will be the time parameter. Okay. Thank you for the question. Right now, right? Say again, sorry? Did you just introduce it right now, or did I just introduced it right now. So now what I'm doing is we have these three variables that are describing coordinates in metric space, and I'm switching these three for tau, x, and y. Okay. So everything I've been doing up to now is just switching coordinates to make some of the aspects of this Hamiltonian constraint clear. Okay. Okay, so now, this will be the final coordinate transformation we do, and this will be the form that we'll care about. Okay, so there might be some additional factor here that I wasn't too careful about, but it's not super important. Important part is you have some kinetic term, have some potential term, and as you can see, because of this coordinate transformation, this tau coordinate now has this minus sign in front of it, so we will interpret this tau as this tau as the time that we will parameterize x and y with to describe the dynamics. And then what you see here appearing is nothing but the metric, is related to the metric in the upper half plane representation of 2D hyperbolic space. Okay, which from now on I'll just call H2. So the way why I'm saying this is that, again, if you write down some Gij related to these pi's, this metric here that comes in front is nothing but the metric of 2D hyperbolic space in the upper half plane representation, so where the coordinates are the usual x and y, where y is only positive. So hopefully you're familiar with this representation, because this will be the starting point, and we're going to use it a lot. So just tell me if you're not, but there's not so much more I can say about this. It's just one of the representations of 2D hyperbolic space. Okay, so that's about kinetic terms. So that's how we see this hyperbolicity come in, and this tau will be our time coordinate. But then importantly, why did we do this? Why wasn't this set of coordinates already sufficient? The point is that if you look at the potential, which I haven't derived here, right? I'm just quoting. It looks something like this in these coordinates. And importantly, the time and the xy coordinates, they decouple inside the exponents. So the reason that we have exponents is because we started with exponential scale factors in the metric ansatz, like the way we were writing the metric. But the important point here is that using this type of parameterization for the metric components, we get this separation between what we will use as time coordinates and the x and y. And in particular, when we're close to a space-like singularity, we know that, right, intuitively, the volume will become small, right? That's the whole point of having some singularity, is that space collapses, space-time collapses, and the spatial volume will be going to zero. And if you were to go through the details, you would see that the way in which this happens in terms of this tau is that the volume goes to zero as tau goes to infinity. So in the near singularity regime, this thing becomes super big, and that means that these exponential terms in the potentials will become either infinity or 0, depending on the sign of these guys, of these W's. So the reason I'm calling them W's is because they will end up being the walls in our 2D hyperbolic space. Okay, and how do we understand that they become the walls in hyperbolic space is precisely due to the fact that these guys are either 0 or infinity, depending on the sign of W. So effectively, in the late time regime, when this applies, these exponential terms are basically infinite Heaviside functions for these functions. And again, these coefficients we won't care about. They just have the right sign so that they define exponential walls and not exponential wells. But this all comes from like working through the steps. So let's just make sure that the sign here is right. So whenever this guy gets big, if W is positive, this becomes infinite. So indeed, that's right. And when this guy becomes negative, it's all suppressed and it becomes 0. So that's whenever this Heaviside is below the 0 threshold and hence vanishes. Are there any questions about this? So what we find, hence, is that the dynamics of this, what this Hamiltonian constraint tells us, is the dynamics of these metric components. They're basically following some free trajectory most of the time, namely whenever these things are 0. But whenever the dynamics happens to bring you at a point where these W's become positive, you hit an exponential wall and you go back. You had a question?
Yes. In the potential term, in the equation in the box, we have a sum of CI's in front.
Yes.
Right? These CI's are just numerical coefficients or depend on X and Y?
Okay, so they depend on a bunch of stuff. Namely on momenta of various things. I don't think they depend explicitly on X and Y. I think they mainly depend on the thetas and so on. I'll try to be more precise about their dependencies in the notes. But the only relevant thing about them is their sign, basically. And in this case, I can tell you that the signs are such that these things define exponential walls as opposed to wells. Okay. Okay, so now of course, so that's a classical story and how to understand this dynamics in terms of 2D hyperbolic billiards. So then what you do then effectively in the classical story is that you solve this constraint by expressing p tau as a function of all the rest, and so that describes free motion on hyperbolic space with these exponential terms. Now, as I've said before at the very start, we will not care about classical dynamics, we'll only care about the quantum dynamics. And so in terms of this setup, what that means is that you want to quantize this theory. And the way in which you do that in the case of gravity is that you apply canonical quantization to all of these momenta. So you say that pi is the derivative of some wave function that will depend on tau x and y. Sorry. And then here I'm just grouping all of the fields with the, like this could be tau, and then it's p tau and pi tau and so on. So you substitute this pi for this thing everywhere, and you end up with a wave equation that is known as the Wheeler-DeWitt equation. And okay, I'm out of space on these boards. So it's very similar. And of course, given that we don't, I mean, people who know something about gravity might complain then that we don't know how to properly define quantum gravity and so on. But the Wheeler-DeWitt is used a lot in quantum cosmology, and it should be a reasonable approximation as long as you work in the right in the right regime. And so we'll be working in the same classical regime where you can sort of trust just canonical quantization. So when you do that, it's nothing too difficult. Just look at this, apply canonical quantization as I was showing. And okay, what you end up with is I'll just write down the name for those who don't know. So it's basically the Schrödinger equation for gravity. Okay. Okay, so it's equal to 0 is what I wanted to write, but I already wrote it here. Okay. And this function here will depend on tau, x, and y, as written here. Okay. So what you find is exactly the same story, but now you can rephrase things in terms of, like, this potential will basically impose boundary condition on this psi. Just like in the classical story, you had these exponential walls that became infinite Heaviside functions. Now, these things in the late time limit will impose Dirichlet boundary conditions on these walls. So the wave function will need to vanish on these walls. And for the rest, it's exactly the same. You have some wave equation with here the canonical hyperbolic Laplacian in 2D. But the fact that you have these Dirichlet conditions here means that you have to solve some quantum evolution on some hyperbolic billiard with these walls. And so now I haven't told you yet what these WIs are, and that's what I'm going to do next. And the whole point is that these WIs define a specific type of billiard that will give rise to these anomalous statistics. But the important point to notice is that although some, people who worked on hyperbolic billiards before in the setting of quantum chaos might have thought that hyperbolic billiards are maybe some mathematical curiosity that you could try to compute things of, but that aren't really realized. They're definitely realized in some settings that describe, for example, near singularity dynamics. Okay, so what these walls look like is, okay. Okay, so they will define Dirichlet conditions on the following locations on the xy plane. Okay. Dirichlet condition on the xy plane, they look like this. Okay, so the first loci will be this, the second loci will be x is 0, and the third one will be x is 1/2. So this you can in principle derive if you were to do all these steps and isolate whatever the potential terms are that will give you the smallest domain. Okay, and the main point is that this thing, if you were to plot it, what it looks like is something like this. Okay, so the billiard is defined whenever you're above this line and in between these two lines, where this is x and this is y. Okay, so
is there some motivation for choosing exactly that region from gravity
Well, so we're not choosing anything, right? That's what follows. Like if we were to do the steps, those are the WIs that would come out of doing all of these steps, so computing the Hamiltonian and so on. The potential that comes from this action with this parameterization for a metric is precisely these walls. And the fact that WI has to be positive tells you that the region where the motion happens is inside this domain. Does this?
Sorry, so like how? So you have some explicit WI, and then just imposing Dirichlet boundary condition just gives you that polynomial equations for x and.
Yes. So exactly. So just these WIs, what they look like is exactly like. I just don't want to get the sign wrong, so that's why I didn't write it. So x squared plus y squared needs to be bigger than 1. So that will tell you that you have to go up, and then it has to be bigger than 0, and it has to be smaller than. So those are the things that, those are exactly like if you move all of that to one term, this will be one of the WIs. So it's not something you choose, it's something that comes out of the various steps that you do. Okay, any more questions? So this is all motivational, right? It's just to say that this type of billiards emerge in a specific context, namely in gravity. So I guess for everyone in the audience who cares about gravity, that would be the motivation to have a look at these specific billiards. And so this billiard, if you remember the drawing I was making on the Poincaré upper half space, so the first example I was mentioning is the equilateral triangle. So this is not this. But then I made a second drawing where I was drawing these lines, and I was saying that this triangle also has these specific arithmetic properties, and this is this triangle. So if you were to map from Poincaré to from the Poincaré disk to the upper half plane, you notice that the two are the same. Okay. And okay, now we come to a point where we can have a first glimpse at why this domain would be special. And the reason is that this domain is nothing but half of the fundamental domain. So that's the whole thing. So this is half of the yellow, and the yellow is the fundamental domain of PSL to Z. So here I'm writing Z, not R. So these are all the modular matrices, so with integer entries, right? So you might be more familiar with these notations. So G element of this could be written as just this matrix. So this is D. So their determinant is 1. And A, B, C, D are all integers. And on the upper half plane, these matrices act as like this. Hopefully you've all seen this at some point or another. And by looking at this, like what this P means here is the fact that if you add minus signs, they drop because it's a quotient. And so G and minus G is basically the same action on the upper half plane, so we identify them. And the claim is, which is not something we'll check, but it's a well-known fact, that this domain here, so the yellow part, is exactly the fundamental domain of this group. And what does fundamental domain mean, right? Is that, so no 2 points in this fundamental domain are connected by such a matrix. But this domain, when acting with all the matrices of PSL to Z, tessellate the whole upper half plane. So on any point on the outside of this domain can be brought inside this domain by the action of one such matrix. So that was what it means to be a fundamental domain of PSL2Z. And our billiard here is half of it. And that's actually, so that's where the arithmetic part of the name comes from the fact that this Z appears here. And, well, most of these, at least the most easily understandable arithmetic groups or arithmetic billiards originate from the fact that their domain, so where the billiard motion happens, is related to the fundamental domain of a subgroup of PSL2Z. So those are the most easy understandable cases, and it'll also be the only words that I say about generic cases, because it can be increasingly difficult. So what we'll do is try to understand arithmetic chaos from the point of view of PSL2Z, because that's the most canonical, like the canonical example. If you read things about it, most probably it'll be about PSL2Z. But just know that there's other examples. For example, this equilateral triangle is an example where, in that case, it would be related to a subgroup of PSL2Z. Are there any questions? So there's one more thing I'll discuss in relation to this, because at this point we still have, where is it? We're not quite yet at the description where we want to be, because we still have this time that is not, like I've just been saying in words that I'm going to use this time to parameterize the motional hyperbolic space, but I haven't quite solved this equation yet. So that's the next thing we'll do. And then we'll see the Laplacian, like the eigenvalue problem onto the hyperbolic space emerge. And from there, so that will be the goal, to try and understand the properties of this motion from the quantum chaos point of view. And that will be the end of the motivational part, and then we'll be able to say some more interesting stuff. So if you were lost in the gravity aspects, now is a good time to reconvene. And okay, so one of the important things here is that because this is half, because the billiard domain we care about is half of the domain of PSL2Z, we will be interested in so-called modular invariant functions. Well, maybe I should say something else before. Okay, let me just first solve this equation as I was going to say, and then I'll say what I wanted to say. Okay, I'll just erase things here. Oh. Okay, so we want to solve the equation, the Wheeler-DeWitt equation, basically. And a straightforward way to do this is by using separation of variables. So we write, tau xy as, we'll write it as, a function of tau, and then a function of x and y. You substitute it, and then you try to solve. So when you do this, you find that the generic solution looks like this. So some coefficients I will call like this. So we want to sum over all possible okay, I'll just write it down and then I'll comment. Okay. Okay, so if you substitute this separation of variable to this equation, you find that the generic solution looks like this. So that is the F part here, with specific energies that are related to these functions. These functions have to solve this equation, this eigenvalue problem with the energies appearing, the energies K and appearing both here and there, right? So that comes from solving this equation. That's something you can just check by substitution. And this eigenvalue problem is what we are going to be interested in. Specifically, of course, with the conditions that psi has to vanish on these loci. So psi n xy has to be 0 on these regions in the upper half space, upper half plane. So you have eigenfunctions of this Laplacian that you have to solve for, and that's pretty much the eigenvalue problem in the quantum theory. So in a quantum theory, you want to solve for eigenfunctions of the Laplacian with, well, you're trying to find the energies that correspond to these solutions, and then you can plug that back in and you find a general solution to the width equation. So this is the last time we're going to really talk about this time here, because for now on we'll just be interested in wave functions defined on this two-dimensional space that solve this Laplacian eigenvalue problem. And now I can say what I wanted to say before, namely the importance of the fact that the billiard domain that corresponds to these balls here, the fact that it's half of the fundamental domain of PSL2Z means that these wave functions here are actually if I use the coordinate, the usual coordinate on the upper half plane that I was also using in these, sorry I didn't define, but hopefully people have seen it enough that it was making sense regardless. So the wave functions here will have to be invariant under any of the modular transformations. So they will have to satisfy this, precisely because this billiard is half of the fundamental domain of SL2Z. But of course, not every function that is modular invariant will give you the right boundary conditions. What you have to impose in addition is that it vanishes on x is equal to 0. So you have to impose some reflection condition. Okay, I'll say a few more words. Oops. So you will require, okay, so you can see that the modular domain has, so the fundamental domain of PSL2Z has some parity transformation or parity symmetry. So if you look at the right of this line or the left of this line, there's a transformation that moves them into one another. This transformation is exactly z going to minus z complex conjugate. And for the wave function to vanish on the x equals 0 line, you require this wave function to be odd under this transformation. So we will care about modular invariant functions that are solutions to the Laplace equation that in addition are odd under this reflection transformation. And then you can show that in fact, using modular symmetry, the fact that it's odd under this transformation also tells you that it will odd under reflection of the other three walls. So that's an exercise that I will not work out, but that you can try to work out. And we could also do it in the tutorials if you wanted to. So specifically what you have to show is that if you assume this, So you assume that you only care about the odd modular invariant wave functions, then you can show that these functions will also have to have this transformation property that I'm going to write down now. That's the first one. That tells you that it vanishes on the most right vertical line. So at x equals, so vanishes at x equals 1/2. And also this implies, this together with modular invariance implies this, and this tells you that it has to vanish at this locus. Okay. So if you have these two in addition to this, you find that these wave functions indeed satisfy the billiard problem. And so what this means concretely is that although from the gravitational point of view you should be solving for the billiard problem that you got from the width equation and so on, what we'll be focused on mainly is trying to understand the spectral statistics of these guys here. So those are the energies of the eigenvalue problem, right? So we'll be interested in understanding the statistical properties of these guys and why they're anomalous from trying to understand modular invariant wave functions. And then, of course, you want to impose oddness thereafter, but we'll try and see how much time we have. The main point is that the main steps and so on appear here, and most probably we'll only have time to do this, but then in the notes I'll definitely try to make the billiard problem specifically clear as well. Okay, so what we want to do now, the problem is to try to understand this type of eigenvalue problem, hyperbolic Laplacian on the upper half plane, and that requires you to understand for what values of these energies Kn you can actually find a solution. So you can, in principle, write down, expand this in Fourier modes for the hyperbolic Laplacian. What it looks like is something like this, where you see some Bessel functions up here. And then some signs. So these here are the solve the Laplacian equation with a specific value for Kn, but with the boundary condition that you impose, so that the wave function has to vanish on the three walls. There's only so many Kns that actually solve the full Laplacian equation with the boundary conditions. So the task is to find the Cn's for which this guy solves the Laplacian equation for specific discrete values of this Kn. Okay, so then like solving the billiard problem amounts to finding sets of CNMs and the corresponding Kns, which are the energies of the problem. And so when you look at spectral statistics, for example, you care about the statistics of the energies. And we will see that these are anomalous. So if I have some minutes left, 5 minutes left, I'll try to sketch the spectral statistics. And then what we will care about, hopefully in the last lecture, is about what we can say about the actual wave functions in addition to the eigenvalues. And so we'll focus in the last lecture most probably on whether the chaos lies in here, because we know that, well, we will see that it doesn't seem to appear in the eigenvalues. Okay, so that's roughly the plan. So then let me just sketch the let me just sketch what the spectral form factor looks like. So I guess not everyone might know what the spectral form factor is. So maybe I'll just already say a few words, and I'll have to talk about it again next time anyways. But okay. Let me already get a few things out of the way now. Okay. So you might have heard from other more recent works as well that what the spectral form factor for chaotic models look like is usually it looks something like this or something. So that's, as I will say, as I will be clear next time, I'm not going to care about this part. So we'll look at something that's slightly different from the usual one, where we basically remove the initial, the data that gives you the initial. So this is known as the slope. Then you have like a dip. Then you have a ramp. Then you have a plateau. So you can write this down in your notes if you want to. But we will not care about the slope. So we will define a subtracted spectral form factor, where the slope is, it's not relevant for whatever we want to say. So you can imagine that it then looks something like this, where the ramp and the plateau are the defining features that you would want to see in some chaotic model. So this thing here tells you, well, again, I'll define it next time, but it tells you something about the statistics of eigenvalues, these KNs, and how they're statistically correlated. So if you compare it to like some integrable model, for example, so that's chaotic, and that's integrable. What it looks like for integrable models is something like this, where the timescales where it reaches the plateau are completely different. So in this case, it's sort of 0 at very short times, where the timescale here is controlled by the time, the period, sorry, of the shortest periodic orbit in your classical system. So we will call T min. And usually, like in billiards, you can show that it grows in this way with the energy. So at high energies, at high Ks, this is pushed to 0, and you pretty much have the plateau. Like if you had just a plateau for all times, it would be telling you that all the eigenvalues are statistically uncorrelated, which is usually what we assume to be true for integrable systems because of all the conserved quantities that are there and that separate your eigenvalues into distinct sectors. Okay, so roughly the thing to have in mind for integrable models is that pretty much all the time you have this plateau, and only at very, very short times, at the order of the period of the shortest orbit of your classical model, you find something that deviates from this one. And the height here is related to the mean density of states at K. And the same holds here. So I'll just say one more thing here, is the fact that, okay, I should really write energy here, but anyway, it doesn't matter too much. Don't be confused by this. I'll explain more next time. The main difference that we want to understand in this set of lectures is that for arithmetic chaos, what you find is completely different than this. Namely, you find something that grows exponentially. And then reaches the plateau super fast. So the time scale here is something like log k over k. And it's sort of the same time scale as here when, I guess roughly when the, okay, well, let's see when the ramp starts. But this time scale here is much longer. So I'll say more about it next time. But the main point is that here you have, for arithmetic chaos, you have this exponential initial behavior of the spectral form factor. And it reaches the plateau, the usual plateau, as in any of these cases, much faster than for usual chaotic systems. And it tries sort of, because this time scale goes to 0 as k goes to infinity, you see that it sort of tries to mimic the integrable models much more than the chaotic models. Even though the classical theory is just completely chaotic, like it's ergodic, you can prove things which you cannot prove in most systems. So it's definitely chaotic in the classical case, but somehow the spectral statistics do not happen, do not seem to show this. And so, okay, what we'll do next time is, I guess the next 2 lectures will be about trying to understand this shape. So I'll define the spectral form factor a bit more, and we'll try to understand how it comes that you seem to be closer to integrable models. And as I said in the 4th lecture, we will look at the wave functions, because we don't see any chaos in the eigenvalues apparently, or a very different type of chaos. And so the question we will try to address there is, in the 4th lecture, is whether you can actually find some chaos in the wave functions as opposed to the eigenvalues. Okay, so that's it. So thank you, and see you a bit later. Well, so I've only been saying arithmetic quantum. So I've never actually said quantum chaos. Like we're looking at probes that are supposed to tell you, like, that are supposed to diagnose whether something is chaotic along the usual lines of what we call chaotic. And what we find is that the spectral statistics probes do not seem to say that this system is chaotic. But we know, I mean, this is perturbing because we know from the classical setting that it is chaotic. And that's also why in the last lecture I want to talk about the wave function, because there is actually some signs of chaos. But somehow, because of this relation to SL2Z, and that will be crucial, the spectral statistics seem to be not displaying any of this chaos. But it doesn't look quite like integrable either, right? It just has this sort of properties that as you go to higher energies, it goes closer and closer to what it would look like, but in fact something I didn't say, and I won't be able to say much on it analytically either because it's just too involved. You can actually show that there are some oscillations at this time scale here that, I mean, it's not exactly like there's some, it's not exactly like eigenvalues are totally uncorrelated, but it's definitely not this story either. And I guess it took some time to understand. Like the first thing people saw was whenever I was looking at level spacing statistics, for example, I seem to find Poisson instead of Wigner-Dyson. And then second thing you can look at is spectral form factor, try to understand where this is coming from. And then try to understand this analytically is a bit easier than trying to understand level spacing statistics analytically. So then that's why we'll be focusing on that. And hopefully if it converges towards plateau at high energies, that sort of means that at high energies you will find Poisson statistics. And so that explains then the observations that people made.
Maybe just a continuation and a general curiosity, but about other measures of quantum chaos in the system?
Such as
OTOC or any other time?
Yeah, so okay, I don't know of many computations of that sort. Whenever people were interested in it from the gravity point of view, I think one of the issues was that it sort of depended on what sort of time you were using because you know it's exponentially growing in time, and because you're free to choose whether It's not like in quantum mechanics where you have a given time. In the setting of gravity, you were free to choose whatever time you had, and then people found different Lyapunov exponents classically. And so it was a lot of confusion at that point. But in the quantum chaos, in the quantum problem, I actually don't know any paper that computed any of this, but you sort of face the same type of issues. So I guess that's all I know about this type of questions.
Sorry. Are there any three parameters in matrix that are like tunable to either one of these, to more integrable or more chaotic?
Well, in principle, you could vary the. So I was mentioning that on the Poincaré disk, which is just easier maybe to draw, you could think about, okay, so suppose you have this one, right? Oops, gotten from these lines. So suppose you have this one. It has specific angles, right? That's what defines a triangle. You could try to vary slightly these angles and see how, like, and compute spectral statistics or whatever, and see how these move as you change those angles, because then it's only for specific angles that you find this arithmetic chaos, because it has to be related to domain that is related to a SL2Z or a subgroup of that. So then if you move these angles, you would go away from this arithmeticity, and yeah. So that's the only way I can think of it sort of tuning.
Well, it seems there are no more lectures, so yeah, let's thank Marin for the first lecture. Again. And if you have not signed the list, please sign it. It's just outside. There are already boards for posters, so if you have a poster with you, please post it on the board. There are some pins. And we start at 11, the second lecture.